The objective of reaction engineering in this project is to propose suitable type of reactor and catalyst used in the reaction. For reaction of SMR and WGS, both are using packed bed reactor (PBR). Reaction of SMR is complex reaction. Diffusion of reactants occurs through bulk of gases to the surface of catalyst and porous particle. For the catalyst, nickel oxide is used for SMR reaction since it have high reactivity, withstand a high temperature, and exhibit good mechanical strength. Due to this high catalytic activity and low price, nickel oxide is selected as SMR reaction catalyst. Stoichiometry table for 1 mole of methane and 1 mole of water producing 1 mole of carbon monoxide and 3 mole of hydrogen gas is developed as shown. All the kinetic data are obtained from reference and value used for pressure is 1 atm, activation energy 257.001 kJ per mole, and temperature used is 973.15 Kelvin. For volume sizing of reactor for SMR reaction, PBR volume formula is used in which the conversion is 0.99 and expansion factor is 0.46. Hence, the calculated total reactor volume for SMR reaction is as shown.
Next, the reaction continues as water-gas shift reaction, where carbon monoxide and water are the reactants to produce more hydrogen and carbon dioxide. This reaction occurs in packed bed reactor, and the catalyst used in this reaction is peroxide, which is doped with chromium oxide to avoid peroxide from being crystallizes. This is the kinetic data for the reaction, where the reaction occurs at 400 degrees Celsius and at pressure 1 atm with an activation energy with 89.23 kJ per mole. To start the calculation, expansion factor is calculated since the reactants are gases, but since expansion factor is equal to 0, therefore the volume of the PBR is remain the same, and delta for all species are calculated. Next, Fc0, which is a flow rate for carbon monoxide, is obtained from SMR, and assuming FD, flow rate for hydrogen is 20,000 tons per year, it is calculated for the rate of conversion X is equal to 0.99. Then the flow rate and the concentration for all species are calculated. After that, the yield and selectivity of hydrogen gas are calculated, and it is found that both share the same value, which is 1.003. Lastly, the amount of catalyst needed in PBR in WGS reaction is calculated.
Next part is the way to maximize the selectivity and yield of hydrogen and minimize the side reaction. First method is to increase the concentration of methane. As the concentration of methane is limiting reactant, the entire process will depend on the concentration of methane in the system. So by this method, it can increase the yield for both reaction, SMR and WGS. Second method is to decrease the inlet pressure when the temperature is constant. As stated in the Le Chatelier principle, by increasing the stoichiometric number in the reaction can be favorable in lower pressure condition. So lower pressure system will shift the reaction equilibrium to produce more product. Next method is to increase the temperature of SMR reaction. As the heat of reaction for SMR process is endothermic, which is positive 206.2 kJ per mole, so forward reaction will favor high temperature to produce product. To increase the conversion, the temperature should be increased. And the last method is to decrease the temperature of WGS reaction. WGS process is exothermic process which release heat with a value of negative 41.2 kJ per mole, and the reaction needs to lose energy. In order to favor forward reaction, the reaction needs to be done at low temperature to increase the conversion.
Our objective for process modeling and simulation part is, first, develop mathematical models for the reactor. Second, simulate the steady state reaction process using process simulation software based on process parameter from reaction engineering part. Third, validate the simulation by comparing the manual calculation using reaction system from reaction engineering part and provide deviation area between the simulation and manual calculation. And fourth, analyze and discuss the effect of pressure, temperature, feed flow rate, and composition on the reactor performance. This is our design process flow diagram. In SMR reactor, 1 mole of methane will react with 1 mole of steam to form 1 mole of carbon dioxide and 3 moles of hydrogen gas, whereas in water gas shift reactor, 1 mole of carbon dioxide will react with 1 mole of steam to form 1 mole of carbon dioxide and 1 mole of hydrogen gas. To ease our derivation, we use symbol to represent each component as shown in this table. Before developing the mathematical model, assumptions were made. First, this is a steady state flow process. Second, system is in perfect mixing. Third, system obeys ideal gas law. Fourth, heat capacity and overall heat transfer coefficient are constant. Fifth, this is a well-insulated reactor which heat loss to the surrounding is negligible. 6. Change in potential energy and kinetic energy are negligible compared to other data. 7. Concentration and temperature gradient along the radial direction are negligible. 8. Base component for SMR is methane and base component for water gas shift is carbon monoxide. And the last is the porosity of bed is assumed constant. Rate law of reaction. Since both reactions are elementary reaction, so the rate of reaction in SMR reactor is K1 times C1A times C1B. And the rate of reaction in water gas shift reactor is K2 times C2C times C2B. Now we'll start to develop the mathematical model. First, we'll derive the overall mass balance equation of each reactor using this equation, dm dt equals to sum of mass in minus sum of mass out. And this is the overall mass balance for SMR reactor. Next, we proceed to derive the component balance using this equation, dn dt equals to sum of number of mole in minus sum of number of mole out plus volume of reactor times sum of rate of reaction of the species. And this is the component balance of A for SMR reactor. Finally, we'll derive the energy balance by using this equation. dE over dt equals to sum of energy in minus sum of energy out plus rate of reaction times volume of reactor times sum of enthalpy of reaction plus heat plus work. And since kinetic energy and potential energy are assumed negligible, so energy equals to mass times enthalpy. And QH is the heat supplied by heater, and QC is the heat removed by cooler. And this is the energy balance for SMR reactor. Overall, these are the mathematical models developed for SMR reactor and water gas shift reactor. The first row is the volume profile, the second row is the height profile, third row to eighth row is the concentration profile for each component, and the last row is the temperature profile for the system. Next, these are the consecutive relation, consolidation, and parameters for our design process.
As for the simulation part, the steady-state reaction is simulated using Symmetry software, and data from Reaction Engineering 1 is utilized to simulate the whole process. Two material streams are added, which are steam and natural gas. The mole fraction and properties of the material streams are shown in the diagram above. After that, a mixer and a heater are added into the flow diagram. Both the inlet streams are mixed with the mixer and connected to the heater via two heater streams. SMR reactor, also known as steam methane reforming reactor, is added into the flow diagram. The properties of the SMR reactor are shown in the diagram above. Nextly, a WGS, also known as water gas shift reactor, is added into the flow diagram, and the properties of the WGS reactor are shown in the diagram above. And finally, the outlet stream, which is labeled as CO2 reverse stream, and the properties and mole configuration of the stream is shown above. After the simulation, the values must be compared using manual calculation. Based on the manual calculation from reaction engineering part, the value of product molar flow rate is calculated to be 7,280,707 mole per hour. Based on the simulation, the value of product molar flow rate, which is 7,300,000 mole per hour. Deviation error is calculated using theoretical values and experimental values. Based on the calculation, the deviation error is 0.265. Thus, the deviation error is considered negligible and the assumptions are valid. Next, to analyze and discuss the effect of pressure, temperature, heat flow rate, and composition on reactor performance. This is done using case study function in Symmetry software. The independent variables are inlet pressure, inlet temperature, inlet molar flow rate, and composition of methane on inlet stream. And the dependent variables are mole fraction of each component in CO2 reverse stream, heat energy supplied at heater, and cooling energy supplied at cooler. The first independent variable, which is the inlet pressure. Inlet pressure does not affect the mole composition of each component in the outlet stream, and the heat energy supplied at the heater decreases as inlet pressure increases, and cooling energy at cooler increases as the inlet pressure increases. So to conclude, increase in pressure of heat reduces the reactor performance, since the increase in duty of cooler is more than the decrease of duty in heater. The second independent variable, which is the inlet temperature. As you can see, inlet temperature does not affect the mole composition of each component in the outlet stream, and heat energy supplied at the heater decreases as inlet temperature increases, and cooling energy at cooler remains constant. So to conclude, increase in temperature of feed improves the performance of the reactor. As for the third independent variable, which is the molar flow rate, as the molar flow rate increases, the mole composition of methane and carbon monoxide decreases until it peaks at 9.38 times 10 to the power of 1920 and starts decreasing again. Other components remain unchanged. Heat energy supplied increases as the molar flow rate increases, while cooling energy supplied increases as the molar flow rate increases. To conclude, increase in flow rate reduces the performance of the reactor. As for the final independent variable, which is the composition of methane in the inlet stream, when mole fraction of methane of inlet stream increases, the mole fraction of methane, water, and carbon monoxide at outlet stream decreases, while mole fraction of hydrogen and carbon dioxide at CO2 removal stream increases. The heating energy supplied increases as the mole fraction of methane increases, and also the cooling energy supplied increases as the mole fraction of methane increases. To conclude, reactor performance is reduced due to increased duty in heater and cooler.
Hello, I am Akila and I will be continuing to the next part of this integrated project, which is Chapter 4, CEB 2063, Separation Process 2. In this chapter, we will be focusing more on the last part of the whole process, which is the CO2 removal unit as well as the H2 enrichment unit. In order to gain pure hydrogen, we need to remove all the impurities present in the product stream. Hence, a unit operation known as pressure swing adsorption (PSA) is being utilized to remove these impurities from the mainstream to produce a high purity of the hydrogen gas until 99.9% of purity. PSA unit consists of multiple adsorption columns to ensure the production of the high purity hydrogen is in a continuous process. The column will be placed vertically as the stream in the gas phase. It will enter at the bottom of the column and flows outward through the adsorbent and exiting as the top stream. Second, it is also in series arrangement to avoid the pressure drop across the columns. Next, there will be 5 different mass transfer zones present in the column to adsorb different components. The diagram will look like this. The difficulty to adsorb components is increased as the stream ascending through the bed. Carbon monoxide will be the most difficult component to adsorb as it is almost similar to hydrogen. Adsorbent used in the system would be MOL-SIF Zeolite 13X as it is mainly used for drying and purification of raw gas in separation unit, where water and carbon dioxide will simultaneously remove. Furthermore, zeolite also has a good CO2 adsorption capacity and selectivity at low pressures as well as moderate temperatures. It is also outperform activated carbon in post-combusting operating conditions. In addition to that, the best model for the adsorption is found to be the Langmuir adsorption isotherm. It is being used as it is the most common type of adsorption that were developed based on the theoretical basis and is the most relevant model for practical applications. Next, the process is a physical absorption process where the molecules of the impurities be adsorbed only at the surface of the zeolite 13X. The properties of physical absorption would be first, an exothermic reaction, which is heat being released to the surroundings. Second, no activation energy required for the process to occur. Third, a reversible process where it is affected by the temperature and the pressure of the surroundings. And last but not least, the rate of adsorption depends on the surface area of the adsorbent. The next part will be discussing about the strategy to achieve 99.9% purity for hydrogen production as it has high demand in many industries, especially in chemical industries. Some of the strategies would be: first, decrease the adsorption time. The longer adsorption time gives higher recovery but with lower purity due to the longer contact time. Some impurities might break through the column and mix with the raffinate stream, resulting lowering the purity of the hydrogen and increase the total hydrogen recovered. Hence, decrease the time will increase its purity. Second, increase the surface area of the adsorbent. When the adsorbent has a larger surface area, more impurities will be able to be adsorbed on the adsorbent surface as there will be increasing number of adsorbent sites. Hence, the purity of the hydrogen will be increased as more impurities were adsorbed from the raffinate stream. And third, decrease the adsorption temperature. It is recommended to decrease the temperature of the column as physical adsorption process is an exothermic process. Based on the adsorption theory, adsorption decreases with the increment in temperature as molecules adsorbed earlier will tend to dissolve from the surface at elevated temperature. Hence, decreasing the temperature is suggested to increase the adsorption rate, but lowering the temperature until it reaches below 10 degrees Celsius should be avoided as negative impact of low temperatures will occur.